All right, boys and girls, welcome back to the drive-thru on a special Who Day edition, Monday Night Football edition of the drive-thru. I know you guys are not watching the Bengals right now because you can't wait to watch this quick little drive-thru. Hopefully you'll find it in your busy schedules to watch this video and check out a couple plays of the Bengals as they try to defeat the Texans tonight. But here we go. This is kind of a remix. Nothing that I am about to tell you is new, but we've learned a lot, so let's do a review. Okay? How do we define the equation of a plane? What defines that plane? Well, if you remember, it was like a magic carpet ride. So we needed a vector that was orthogonal to the plane, and we needed a point that was in the plane. And if we had those two things, we could define the plane as A times, let's call this x1, y1, and z1. A times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. Remember that a plane was defined by a vector that was orthogonal to it, and in order for that to happen, this vector, which could be, which could be combined by these, the dot product would have to equal 0, and that's kind of how that happens. So, hopefully you remember how to find the equation of a plane. Okay, so remember that because part of what we're doing today is tangent planes, so we need to be able to remember how to find the equation of a plane. Okay? What about the equation of a line? Well, that was actually trickier than you would think. Okay, what we needed to find the equation of a line was a point on that line, again, x1, comma y1, comma z1, and a vector that was orthogonal to that line. And we will call that A, comma B, comma C. Okay, well from here is where it got weird, if you remember this. We would start with these symmetric equations. I'm sorry, not symmetric equations, these parametric equations. So you'd say x equals x1 plus at, y is equal to y1 plus bt, and z is equal to z1 plus ct, okay? Where x, y, and z describe every point that is on this red line. x1, y1, and z1 are our initial point that we knew, and a, b, and c are called the direction numbers. Another way to write this would be to solve to t, and you get x1 plus a over x equals y1 plus b. Oh, is that right? Am I doing that? No, it's got to be a minus. Let's see. X, totally wrong. X minus x1 over a. Holy smokes. X minus x1 over a is equal to y minus y1 over b is equal to z minus z1 over c. Did I do that right? Yes. Okay, so these are the parametric equations of how to represent a line. And these are called the symmetric equations of how to represent a line. Once again, not that easy. Okay? Next, level curves. Well, hopefully you remember, like if we had f of x comma y is equal to the square root of 16 minus x squared minus y squared. Well, hopefully you remember that is a hemisphere. That is a function. This surface looks like this. Oh dear. Oh. All right, 1, 2, 3, 4. Okay, that's what the surface looks like. And if we looked at its level curves, they would be like looking at above. If we just laid those out, if you'd let like this equal 0 and 4 and 8 and 12 and 16, if you set that equal to this function, well, then you get our level curves. I'm not going to do all this, but hopefully you remember that it would look something like this. Okay? Level curves. Now, please remember that the gradient vectors are orthogonal to the level curves at every point. Okay? That's going to be really important. So the gradient vector is going to either point that way or that way, depending on our surface. Just remember that. The gradient is a vector, and it's orthogonal to the level curve. How do you determine orthogonal to a level curve? Well, you just imagine a tangent line, and you make it orthogonal from that. Okay, so far, all review. Moving on. Level surfaces. I'm starting to realize that everything I skip in this book comes back to haunt me. So, we haven't really addressed this because I thought, well, level curves are hard enough to understand. Why am I going to make these kids try to understand level surfaces if they don't even understand level curves? But the point is, now if you don't understand level surfaces, you won't be able to understand level curves. So let me give you a for instance. What if we had x squared plus y squared plus z squared minus 4 equals 0. Well, now what that is, and we're going to loosely use this notation, okay? But this could be written as, I know it's not a function, but I'm using the same notation as the book. F of x comma y comma z is equal to x squared plus y squared plus z squared minus 4. Well, if you let that thing, let c equals 0, 2, 4, just to get 3 level things, okay? Well, we'd have 0 equals x squared plus y squared plus z squared minus 4. Add 4 to both sides real quickly, and you get that, okay? Well, the second one, I believe you'd have x squared plus y squared plus z squared equals 2. And on the third one, you'd have x squared plus y squared plus z squared equals 0. So if you look, these are now no longer level curves, so we are not slicing them with a plane, but they are now level surfaces. So I'm going to have to try to sketch this thing. So we would have the first one, the radius would be 2. Oh, that's not good enough. Okay, so here goes nothing. Alright, so maybe you can see that little globe, like the Terror Dome where the motorcyclists ride around in circles and don't kill each other because they're brothers. They're always brothers. Anyway, the second one, our radius would be radical 2, which is like 1.7, so that's going to be right here. And let's go to blue on this one. Here, and here, and here, and here, and here, and here. So you got something like this, and this. Okay, you'd have like a sphere inside of a sphere, and then the third one would be like just a dot again. Okay, so those are called level surfaces. Why am I just now deciding to teach you about this, you might ask? Well, because now what I need you to understand is that if I found the gradient of this function, okay, well, what would that be? It would be 2x, comma, 2y, comma, 2z at any point on the surface. So let's say we're taking the gradient of the red function at the point right here. At the point 2, 0, 0, you get 4, 0, 0, which is this vector right here. Oh, cool. It is still orthogonal to our curve. Anywhere we take this gradient, if we figured out what this one would be, that vector is going to be tangent to the surface at that point. Okay? And another way you can think of that, only because it's a sphere, is that it would be pointing towards the center, actually away from the center of the sphere. That's what would make it orthogonal to the sphere. So, remember that the gradient, this is confusing, is orthogonal not only to the level curves, but it's also orthogonal to the level surfaces. And if you can understand that, then now I can teach you today's lesson, which is finding tangent planes and normal lines. Let's pause the video and see if that's enough for you guys to now read through your book and try to do tonight's assignment. I really think it is, okay? But I'll help you through it during class because it's time to get to the game. Boom!